Let's take a closer look at arcs and all types of arcs. First of all, we name some specifically. We have what we call a major arc, we have a minor arc, and then we have a semicircle or a semi-arc. Now, each of these kind of represents different ways to think about the arcs of the circle. Now, you know what an arc is. It is a piece or portion of a circle's circumference. And so when you have points like DE, part of the confusion is if I said arc DE, most of us would say, oh, that's this one he's talking about. Somebody might say, well, wait, it's this other arc he's talking about. Because a circle is connected in one round, you can get from D to E two different ways. And so we need a way to help people to know, are we talking about the little way or the big way, basically. So here's how this works. A minor arc is an arc that is less than 180. So 180 is half circle, and obviously we are looking at currently DE being less than half of the way around the circle. And so this is a minor arc from here. D to F would be another minor arc. It's not more than 180. When we write minor arcs, we use two letters, and we would just say arc DE, or the measure of arc DE. If we would like to talk about the other direction being greater than 180, if we wanted to tell somebody to go the long way from D to E this way, that would definitely be major because we're exceeding the 180, and so we actually would call that arc DFE. Notice I use three letters. In major arcs, we use three letters, and that helps us to know, one, that it's major, and two, the direction to go to get there. Notice if I start at D, I have to go through F on my way to E to accomplish this particular naming convention. And a semicircle is the obvious one that most of all of us know. A semicircle is unique in that, of course, it equals 180 exactly, and it doesn't matter the direction you go. And I think because of that, they accept lots of different things. You can use two letters. You could use three. So it's not really a major or a minor, is it? Because one is defined as greater than or less than 180. And we are exactly 180 because we know we're 180 because we are we sit upon the diameter, right? That helps us to know that that's a 180. You can use either of these are acceptable. There are actually two ways to measure the arc of a circle. You can measure it, like if we wanted to measure this, we could measure its length. That's known as arc length. And basically, the arc length is it's like a percentage of the circumference, pi times diameter. And so sometimes we're interested to know how long is it from here to here. That's not exactly the measurement we're interested currently in, though. We're going to be more interested in what we call the arc angle measurement. And think of it this way, that the idea is now, instead of measuring how long that is, we're going to measure how much of that, of the total 360 degrees in a circle. So, you know, halfway is 180. So I don't know, maybe this is 140. This is known as the arc's angle measurement. And we will be working with that and not so much with this at this stage of the game. So know this, that there's 360 degrees in a circle. 180 is cut by a diameter. And then obviously we'll add and subtract other things to obtain other measurements. Here's a fun little example. These are like little puzzles. So a couple things we don't know. I notice I don't know the arc from E to F. But I do know some things that are going to help me. I know that this is 34, this is 53, I know this is a diameter. So if I was to take 180, which is the semicircle here, the semi-arc from here to here, and subtract these two values, I would obtain the arc EF, which would be a 93 degrees. So I can write that in to help me out. Now CE, let's look at CE. CE is actually simpler than that, isn't it? Let's take a look. CE would be these two arcs added together, and that's just 87. That's very nice and easy. Now the next one is arc ECK. Now that's a major arc that starts here and works its way along. Now the problem with this, I can add this and this. My problem is I do not know these measurements here. But I do notice that 3 of them make up 180. So they each must be 60, aren't they? So this would be a 60 and a 60 and a 60. So to get my answer of my arc from E to K through C, I would take 34, 53, 60, and 60. And if I was to add those together, I get 207, which is a major arc, which makes sense. And then the final one, what do we got left? D, F, C. Now the fun thing about D, F, C is it's all of this. Now, some people would say, oh, that's easy. Let's add the 34 and the 93, the 60, 60, 60, and so on. Another way to do it is just subtract 53 from 360, isn't it? And that would give you that 307 as another way to get that answer. Either way is fine. We also learn here a very important connection between what's called the central angle and the arc that it subtends or sits upon. Let's look at these two regular polygons. We do know that a regular polygon, like an equilateral, divides a circle into 3 congruent parts. So I know that there's 360 degrees. When I divide by 3, I get 120. That would mean that this would be 120, this would be 120, and this would be 120. It also means, listen carefully, that out here this is 120, and this is 120, and this is 120. Do you kind of see a neat connection there? Is that the central angle, how it's divided or cut up, also tells us how much of the arc that it sits on is here. So because this was cut into 3 congruent parts, there would be 3 congruent arcs out here. Here you know this to be 360 divided by 6 to get 60. And so you guessed it, each of those little angles in there would be 60, and that would be how the arcs along the outside as well would be cut up into little 60s. So we're learning a very powerful connection between a central angle and the arc that it sits on. This 60 subtends this arc, and so 60 and 60. The central angle will always equal the arc value. Let's formalize that then. So here's the arc that subtends this angle ABCD, this central angle ABCD, central angle goes to center, subtends this arc, sits on this arc. So what I just discussed with you is that whatever this angle is, let's say this is 58 degrees, what it means is that's how much of the circle's arc measurement, angle arc measurement, is also taken up by that. So no matter what you have for a central angle, if this is 141, that means this would be 141 as well. The arc that it subtends or sits upon will always be the exact same value as the central angle, or vice versa. It's a very simple math because they're equal, but very important idea. Without looking at what they want me to do, I'm going to do a few things. I know that this has got to be 39, and the reason I know that is the central angle is 39, so that arc is 39. I notice the dash marks here and here, which also tells me this arc is 39, but it also tells me the central angle is 39. Another thing I notice is this arc is 70, which means its central angle would also be 70. Now I'm in just a normal situation of just solving for unknowns. This is a diameter. I can see that. It goes through my circle B, through its center. And so I'm able to do a little bit of math here, and I would see that this is a 71. And how do I know that? Is because these three guys have to add up to 180, don't they? My arcs all have to add up to 180, but so do my central angles in that particular case. That also tells me what's left over here would be 141. I'm sure now we have everything we need. Let's see. They want us to find AC, and that is the 39, the arc AC. That was easy, right? It's the same as my central angle. They would like us to find arc AE. A to E. Let's highlight that as this stretch right here. And that becomes a nice easy 141, doesn't it? And all I did is subtract 39 from 180. Let's see what they want now. EK, E to K. E is here. That's this shorter minor arc, and that is just a 71. That's what's left over there. And then finally, the angle. Notice it's the angle KBD, KBD. And that angle would also be the 39 to match that arc there. Central angle is equal to the arc value. One last example. This is a regular hexagon. So again, there would be 6 of these congruent triangles. And so the central angles in here would be 360 divided by 6. So they're all 60. Every one of those little guys would be 60. And as you know, if they're 60, the arc angles out here would also be 60. And so let's put all that in. At least what I can fit. 60. Okay. Let's see what we know now. ATB. Let's see. ATB. 60. That's nice. Next one. DTB. Let's see what DTB wants. DTB. 2 of those, right? 2 of those guys. So that's 120. A to C. A to C. That is also out here on the arc. A to C. It's 2 groups of 60. That is also 120. ECA. ECA. We're doing an arc here, aren't we? So let's highlight that with a new color. ECA. This is a major arc. ECA. And that's 180 and 60 more, isn't it? I mean, we can count all those up, but that's just good old-fashioned 240. AEB. Ooh, something's changed. Now, I erased a few things to make this a little cleaner for us to see this triangle. You can see the right angle that's provided. Why is that right angle? That'll come in a later section, but it's given to you that it's right. We knew that this was 60. These are little mini equilaterals. This was 60, and so these are 60. So actually, what I learned is I am in a 30, 60, 90 triangle. So when they ask us about AEB, that's just going to be a 30 degree. Now the rest of the business is going to be review of our 30, 60, 90. AB is a 5. So what that means is this guy over here is 10. Now that 10 is the entire hypotenuse. They would like just TB, which would be half of that. So it would also be 5. And they want EA. Let's switch our color quickly here. EA would be over here, which is the long leg of that 30, 60, 90. And so it is 5 square root of 3. A little switch up there, but kind of some fun review. Good luck with these guys.